Okay, so you see the thermometers? They are on either side. That white line is called the frost line. And the reason they call it the frost line, remember those 4 different types of material I said? Okay. The things that solidify at at hotter temperatures, the rocks and metals, they will solidify on that side. Okay? So the inner planets are abundant with rocks and metals. Why? Because it's too hot for anything else to really stick around and make a planet. Okay? Does that make sense? So as it gets colder, you can have rocks and metals also solidify out there, but out there you can go ahead and get those hydrogen-containing compounds, the H2O, the CH4, the NH3. Those things can go ahead and solidify too. So on the other side of the frost line, it's cool enough. Like I said, you get your rocky stuff, but you also go ahead and get your snow, basically. You can get water to be a solid out there. On the inside of the frost line, water's just going to be a vapor. Water's going to be a gas. Does that make sense? So that kind of ends up with our rocky planets and our gaseous planets in a nutshell. Okay, so our Jovian planets are outside, our terrestrial planets are inside the frost line. So kind of think of the frost line as kind of where, between Mars and Jupiter, right? Okay, and actually there's something called the asteroid belt in that region. Kind of some crumblies that, if you were to take all the little crumblies in the asteroid belt, it wouldn't make a planet. So it's still smaller than Pluto, I think. Okay, so frost line. Early on in the formation of our solar system. Right? Oh, sorry, you need all these. Okay, there we go. The whole slide is up now, I think. Inside the frost line is us, and Mercury, and Venus, and Mars, and outside the frost line begins Jupiter and those. Okay. Not too bad. Okay. So you see a term here, a few terms. Well, I guess maybe just one term to point out. The word planetesimal, is that not adorable? Just makes you want to cuddle it. So a planetesimal is basically on its way to becoming a planet. Okay, so it's kind of early on. And to me, it's living in Iowa. We may not have tides, but we have snow. And so if you've ever taken the snow and made something small into something very large, a snowball, okay, what you're going to see here, kind of the formation or how planets came to be as they are, reminds me of building a snowball. Okay, so you're going to see that. So let's see, planetesimals again. The protoplanetary disk is kind of that thing that's going to become the plane of the ecliptic, basically. And I'll show you this. I wonder if it'll click if I unplay. See if this reminds you of kind of building a snowball. Where's it go? Okay, so you see the frost line. I'm going to click inside the frost line. Okay, and run it. So there it's showing you what should happen inside the frost line. See, you're making your snowball. Gravity, and I think it's more complicated this night. Actually, I've heard different theories about how you get those little particles to ultimately become a planet. Okay. Let me go ahead. Let's click outside the frost line and see how that's different. Run it. Notice we have an additional color there. Inside the frost line, I think we just had gray particles. And if we get to cooler temperatures, we have your gray, which is the metal and the rock. And then we also have the blue, which could represent the water and stuff like that. Okay, so kind of from left to right, you have time. And I'm thinking, was it 100,000 years? I can't remember. I've read it somewhere. How long does this kind of making larger and larger objects, till clear over there on the right you see finally something that resembles our solar system. Okay. And the term is accretion, so I'll kind of, not accretion formula. Is this accretion formula? Okay. So accretion means the packing together of the particles, so you get larger and larger. So the gaseous planets, anytime somebody says Jovian, I hope we're okay with what Jovian planets are. Right? They're gaseous planets. So basically, if finally, on the outside of the frost line, finally you've got the capability of other things condensing that couldn't condense inside at hotter temperatures, that's part of the reason why they're so humongous. And when we study the Jupiter and Saturn, Uranus, Neptune, we're going to see that they have a lot of these lighter gases that didn't condense, but gravity holds them there because they're so massive. The planet is so massive. Formation of a Jovian planet. At some point it's just big enough to go ahead and keep those light gases around. Okay. So, from left to right, the left over here you see kind of the disk of what's going to become our solar system with the sun in the center. Okay. And then out here on the other side of the frost line, you see one of the Jovian planets. And can you see, like, within or around the Jovian planet, actually it almost has its own little disk, okay? And that little disk can go ahead and form its beautiful moons. So this could be Jupiter forming its moons. Okay, solar wind. Solar wind actually has been in, I want to say, in the news. One of the things about the Voyager spacecraft leaving our solar system is basically they are no longer under the influence of our sun sending charged particles out. Our sun has basically petered out. The Voyagers are gone. Okay, they're like a message in a bottle. It's an awesome, and actually the Voyager spacecraft that were sent up in 71, 70, I think they were like 9 months apart in the early 70s. They have information about us. They have like, maps of we are here sort of thing. A message in the bottom. But all stars, like our sun, have, they're shining, like our sun shines, yay! So not only is it shining light at us, basically it is shining this what's called wind in all directions. Okay, it's solar wind. And so I like this little thing. I'm going to show you. When a star, I would love to see the moment when a star goes from being, when a star begins being a star, okay? That's to say when a star begins making energy via nuclear fusion. And when it does that, its solar wind turns on. So check this out. Okay, so it's kind of cloudy and stuff. So the cloudiness basically was before the star turned on, the sun turned on. When you saw the, okay, basically it went ahead and cleared off any sort of loose light particles anyway from our solar system. It's the solar wind that kind of keeps our solar system sterile from like little microbes. Something has to really kind of fight against the solar wind to get into us. So, kind of nice. Right. Okay. So we looked at this earlier and kind of looking at it again. Notice that kind of over there on the left, over there on the right, kind of because time goes from left to right. Over there on the right where you see our solar system, it's kind of not showing the right story. It's not showing you the crumbly stuff. This is to say that there are some of these sort of things are left over. Okay, so we talked about the Kuiper belt and the Oort cloud. Those are what I call kind of crumbly leftovers. We talked about there's a group of asteroids in the plane of the ecliptic between Mars and Jupiter. Those are kind of leftovers that just didn't accrete into something. So they think that early on there was much more chaos in our solar system. Okay, much more large objects hitting each other, which kind of makes sense with the nebular theory. And kind of related to objects hitting each other, okay, they think that most of our H2O that is associated with our planet actually kind of came from icy objects from the other side of the frost line during the chaos. Okay, early on you had water condensing out there, okay, and then these objects kind of zipping back and forth on the frost line. So this sort of chaos early on in our solar system, where big players were kind of whipping through between planets, that actually can help explain poor Uranus. I kind of told you how Uranus is like this, just got whacked. And here in a minute, I'm going to kind of show you basically how our Earth got whacked too, and it tilted our axis of rotation and it created the moon. It's called the collision ejection theory, where the ejection is where we get the moon, and the collision is actually the early on bombardment. So I said Mars has 2 ugly moons. These are Mars moons. Do they look like potatoes? Well, they do. They look like ones you won't eat. Yeah, they're not even
throw out.
good potatoes. Oh dear. I'm pretty sure that these are the Mars' moons. So that's more normal if we were going to have a moon. But this, and it's a busy slide, so let me kind of show you. This is 1, this is 2, and this is 3. Okay? 1, 2, 3. If you've ever heard of, I think it's called Thea, they actually have a name for that. See that red thing? Okay, that's the impactor. Okay, that's the thing that early on they think is responsible for the Earth's moon. About the size of Mars. Smack. I know. Ouch. And then you see number 2, basically with the impact, that took Earth and made us ooey gooey again. I mean, the impact was energetic, it made us hot. So number 2, what number 2 is showing you is if you can kind of see it's molten, because it's red hot, but also see kind of some debris here. Basically, what created our moon was kind of the Earth kind of taking some of its stuff and kind of making a little kind of accretion disk around. And that's what you see at 3. Okay? So kind of finally things settled down, but it basically spit up our guts, and that became the moon. One of the things about the moon is made up of similar stuff of Earth's crust, and that makes sense to this. Because basically before the impactor, Earth was already starting to kind of have a crust. It got hit, and what's going to get scattered? Well, it's crust. And the moon is kind of like our Earth's old crust. But it's called collision ejection theory of the formation of Earth's moon. Okay, and it's a nice, pretty spherical moon, hefty size. let's see, it says that, number 3, it says less than 1,000 years later. Interesting. Okay, so this is Uranus, and there's the kind of a set of rings around Uranus. And, you know, it just was a casualty of that early bombardment.
On the last slide, was there supposed to be words or was this one? We have like what looks like spaces. We didn't know if there was words.
There we go. There's your words. Thanks. Thank you. Much better. So kind of 3 stages: impact, ejection, and the moon. We used accretion for kind of snowball process. So it's kind of what's happening. Okay. And there's Uranus. And the reason it looks like that is because it is like that relative to the plane of the ecliptic. So, tomorrow. So next week, when we study the gaseous planets, you know, that's one of the characteristics of Uranus, is its tilted axis of rotation. And the thing is, when it orbits the sun, like if the sun's there, it does kind of like the dance thing. So it goes like this, and then this is 1 quarter, okay, and then this is another quarter, and then this is another quarter where this is axis of rotation. So it has really crazy extreme seasons at its poles. Okay,
Okay, this might sound like a dumb question, but since it's like tilted like that, does it still rotate like this or does it rotate like this? Does that make sense?
yeah, it does make sense. It rotates like this.
Okay.
Yeah.
Just because the rings are like from.
Mm-hmm.
Okay.
Yeah. I think we said the same thing. So to kind of summarize from top to bottom, we have the solar nebula, and it kind of has some sort of spin to it. And we're going to see that if a star is going to be born, only if it has some rotation are you going to get a disk that can form planets. Cool. All right. It's kind of funny when I was looking at this part. Remember I talked about carbon dating. Did I talk about carbon dating last week? Okay. So we can't use carbon dating for this because you need living material. Okay, but we can get to the age of rocks another way. And it has to do, again, with isotopes. Remember, what an isotope is basically the same element with a different number of neutrons in its nucleus. But it also has to do with different elements. I know this is a busy slide. Okay, so I'll kind of point out a few things. But you guys, everybody's heard of the element potassium. What's the symbol for potassium?
K.
K, very good. Special K. Exactly. And what you see is that K, potassium, actually will decrease over time. Okay? And it actually, one of its decay products, is argon. Okay? So it breaks down and it forms another element. I'm trying to think of potassium. Argon actually is a really stable element, but anyway. So as your potassium decreases, your argon increases, and we know at the bottom there, we know it's kind of like a clock. I mean, you have to know what you're doing or whatever. I don't know. I have to be able to do the science. But the amount of potassium gone and argon formed, you can date things. Bless you. Okay, so from that potassium decay and argon buildup, we can date meteorites. Now, meteorite is a space rock. We're probably all kind of okay with this. We'll talk more about this later, but a meteorite is a rock from space. And I'm going to try to convince you later, how do we, out of all the rocks that are on the Earth, how can you pick up a rock and say, well, this is a space rock? And how, out of all the rocks that are on the Earth, how can you pick up this rock and say this is a space rock? Okay. Yeah, the assay of it's different. The amounts of stuff in it doesn't match. Or very good, yeah. And along those lines, we know that we have rocks that were basically little pieces of Mars that broke off and it landed here. So, could we track them back? It's just kind of amazing. But once you get over that, kind of a space rock being 4.6 billion years from the time it kind of starts solidified, okay, means that basically the sun has been doing what it's doing for about that long, 4.6 billion years. So that's a way to date our solar system. So that was 4.6. I'm going to throw some numbers at you, but they're all similar. A little bit ago, didn't I say something about our sun has 5 more billion years to live? Yeah, 4.6 billion years. So we kind of have a range here. But our solar system, we think, when we say our solar system is this old, I mean, remember I showed you the solar wind? Okay, to me, that's when the clock starts ticking, when the sun turned on. So are they finding planets around other stars? Yeah, I think if you took this course from someone like me, who's not an astrophysicist, but just somebody at community college, if you took this course probably 20 years ago, they'd say the odds of finding planets orbiting other stars are like, yeah, look at that. But now, it's like we have planets, and we're seeing them right and left. Forget it. So I kind of want to take a few slides to say, how do you know that there's a star out there and there's a planet orbiting that star? Well, actually, closer to home, our own sun, can you see the sun kind of wiggling? Our own sun wiggles a little bit. I know we said that the sun is at one foci of an ellipse, and all the planets, orbit in the shape of an ellipse. But Jupiter tugs at our sun. Jupiter tugs at our sun. So if you were associated with a planet orbiting another star, and you were to look at our star, you would see it kind of move, okay? And you could infer that it's moving for some reason, and the reason is it's got a large planet around it. So that's pretty cool. So then also, we can, remember we talked about the spectra and how electrons kind of do funky things. We can use spectra, like spectral lines, to know what kind of elements we have. It's a fingerprint. Those spectral lines are a fingerprint. Let's leave it there. So honestly, we can look at spectral data coming from a star-planet system and understand what sort of compounds might be associated with the planet. That second one down there, so that was direct. Indirect was what I said just a little bit ago, that Jupiter is making the sun wiggle, okay? So we may not be able, on a distance, on a planet over there, to see Jupiter, but we could infer Jupiter was there. So there's direct detection, indirect detection. I think I said as much here.
Because it's like if I highlight after the pen, it like bleeds and I hate it. So I always have this.
That's good. She's got our little blanks highlighted.
I played ahead. I printed them all out and highlighted them.
Very cool. Okay. Yeah, I don't have a whole lot to add to here. This is just still talking about that indirect detection of the presence of a planet. Okay. Another way, and I guess this actually looks at tugging, is I'll do the whole, we're over there, okay, and we're seeing our sun move, okay, wiggle, and we're like, hey dude, there must be a big planet Jupiter making the sun wiggle. But what if we were over there and the wiggle was like this, okay, and this was the plane of the ecliptic, and we could not see, you couldn't see, it's not, remember we call this proper motion, okay, and we call this radial motion. Okay, you can see proper motion, we can see that wiggle. This is Jupiter, okay, but if we put the sun here and have Jupiter do this, then our wiggle's gonna be here. And if I'm over here, I can't see that. That's radial motion, proper radial. So how do we get radial motion? Okay, the Doppler effect. As the sun is moving towards us, we'll get that blue shift. As the sun's moving away from us, we'll get that red shift. So that was something we talked about in chapter 5. It's a subtle thing, and it's funny, like, what sort of geeks are really into this? Sorry, but you know what I'm saying? I mean, that would be so tedious to, but it would be a rush, wouldn't it? I don't know. Those planets that orbit other stars we call extrasolar planets. And 1995, the first one was detected. The 51 Pegasi, of course, that's, you recognize Pegasus, that moon Taurus constellation. So there's another way to determine there's a planet, and it's called transit / eclipsing. So if somebody says, I'll go back to our solar system, a really fun event, if I don't know when the next one's going to be, but if this is our sun, if somebody says that Venus is going to transit the sun, basically how we're lined up, here's the sun's disk, and Venus is going to go, from our perspective, go through the sun's disk. That's called a transit. I mean, it's not going to go through, but from our perspective, as Venus orbits the sun, okay, it's going to go across the sun. That's the transit of the planet. So just along those lines, very similar, we could be studying a star, and we could actually see its light go down just a little bit, okay? Why? Because there's something going in front of that star. What is it? Well, it could be that we're just kind of looking into the plane, and we're privy to basically a transit event. Okay? The light goes in just a little bit. And that's being shown up here. You see the 3 and the 6, okay? That would be the light from that star going in just a little bit. Actually, the 3 is pretty extreme. Okay. Ooh, this is kind of a fun one. Actually, snapshots. So a lot of times, like, see that circle there? You're like, what in the heck? And what that circle there is to block out the light that you don't want to be looking at. So that circle there is blocking out the light from that star. So we can kind of focus on the next star. So here actually is a photograph of a planet that's orbiting the star. Pretty cool. Pretty cool. So to, I think, just kind of finish up, and if you follow the discovery of other planets orbiting other stars, you already know this, but there's a lot more Jupiters out there than there are Earths. Okay, there's a lot more gaseous ones than there are terrestrial. But is that true, or is it just easier to see the gaseous ones than it is the terrestrial ones? So down there, the Kepler Space Telescope, so that was, we talked about telescopes that are orbiting the Earth, okay, and that's one of them. And that one was designed just to look for planets. Just to look for planets. And it's been doing a darn good job of it. So, when we look at, this actually has three things. It's a very busy plot. There's three pieces of information on here. And they are, okay, down here, how close is it to its star, excuse me. How close is that planet to its star? Okay, right here is how Earth is to its star. And this would be closer, and this would be farther out than Earth. Then here is how eccentric is its orbit. But up here is kind of interesting. The size of the dot, okay, says how it is relative to Jupiter. I think the mass of Jupiter. So, for instance, something this size, with that size of a dot, is somewhere between the size of Jupiter and 10 times the size of Jupiter. Let's see, what did that slide say a little bit ago? Earth is 300, it'd take 300 Earths to equal 1 Jupiter. So, but that's crazy. That is crazy. Jupiter's one big honking thing. Okay, so a lot of information there. And this is dated, so, you know. So this kind of shows you, you kind of see the symbol of an Earth, and then you see the gas giants, by the way. Jupiter's the most giant. Then we have Saturn, Uranus, and Neptune. And so you can see just at a glance that we're just definitely finding more massive planets than we are the smaller ones. So this is probably a little dated.
Can you go back one more quick?
The end. Okay. So you might want to read your textbook to kind of solidify, you know, these two chapters, but we're in good shape.
I missed one slide too.
What's that?
We have chapter
I don't know which one.
Yeah, it's under doc sharing, you know, where you printed those out, it's called a chapter assignment.
Formation of terrestrial
making sure.
planets.
Cool.
Oh,
So
fine.
you said that it takes 7 years to get to,
Okay.
or
I think it might have been even more.
how long does
So
it take?
gravity eventually someone.
Is it like one full year, or what,
I
like,
missed
how?
one. And what was
Because
like?
we got numbers, but how long does it take to get to?
Inside. Okay.
It's a minute.
Thank you. Oh, no, I guess I did right.
See, what do you think?
Which one did you need?
Like, I don't know, I just thought that was weird, but that was stuck in my head the entire time, I was like,
Like, what's weird about it?